and sell it as a virtue. So I'm only going to have a single software organism. My organism is just a program, a computer program. And you pick a programming language, a universal programming language, and your space of all possible organisms is a software space. It's the set of every possible program written in that language. Okay, so this is a fairly rich space. And you have your organism is just software. That's like saying, I throw away the body, just keep the DNA. Okay, so my organisms have no bodies, they just have hereditary information. And I'm only going to have a single organism at a time, no population, no sex. It's a single organism, it's a piece of software, it's a program, it's an algorithm. And it's going to be mutating. And what is its goal in life? You know, what does this program do? Well, what it does is, normally you'd say it has to interact with the environment. And that would be complicated. Or interact with other organisms, that would be complicated. You know, I don't know how to put that in the model. So, but I'm going to put in something like that, like an environment. The point is to give this organism a goal, give it something to do, which means so that you can decide how well it achieves its goal, and that gives you a notion of fitness, and you can use that for natural selection. So normally the fitness would depend on how well the organism does in the environment it is. So in a way, doing this is equivalent to having an organism aware of an environment, interacting with an environment. It's just mathematically easier. So the goal of my organisms are mathematicians, and their goal is to calculate a single positive integer and then halt. That is the goal in life of these organisms. In other words, this is something called the busy beaver problem. It was invented by Tibor Rado around in the 1960s, published in the Bell System Technical Journal, where Shannon published his papers. And the busy beaver problem is the problem of concisely naming an enormously, monstrously big number. And it may seem like a sort of a trivial problem, but it's not. It turns out it's a deep problem which directly involves Gödel completeness, and actually Turing's halting problem. I'll talk about that in a moment, but just first let's just state very clearly the fitness of the organism, of my software organism, is the number it calculates, which will be a positive integer. I'm not interested in programs that don't calculate anything, or programs that go on forever, or programs that calculate several integers. I'm only interested in the program that calculates a single integer and then stops. Otherwise, those are the organisms. Otherwise, it's a bad organism. And the bigger the number a program calculates, the fitter it is. Okay, so that's my fitness criteria for comparing the fitness of two organisms. Now, this problem of naming a big number is actually, to show that it requires creativity, well, sort of an intuitive way of seeing it is if you have a big number n, one way to get a still bigger number is to add n to n. Even bigger number, you multiply n by n, or you raise n to the nth power, or you hyper-exponentiate. You take n to the n to the n to the nth n times. So, in a way, one reason to create these mathematical concepts of addition, multiplication, exponentiation, hyper-exponentiation, and hyper-exponentiation is in order to be able to name bigger numbers, really big numbers, very, very concisely. And it turns out, as you can see pretty clearly, there is no best scheme for concisely naming a very big number, because given any scheme, you can use it to get an even faster growing function. So formally, if you want to prove that this problem requires creativity, as Tibor Rado points out in his 1960s paper, this is really equivalent to solving Turing's halting problem. That's why this problem requires an unlimited amount of creativity. If you wanted to do a formal proof, it's intimately connected with Turing's halting problem. Because these are ways to bound the runtime of a program as a function of its size. And if you had a best possible way to name really large numbers, that would give you a way to calculate in advance how long a program can take to run. So you just run it that long, and if it if it hasn't halted yet, you know it's never going to halt. That's basically the connection with Turing's halting problem. Okay, so what is this little model of evolution then? It's really a rather familiar object to physics. It's a hill climbing random walk in software space. Now, random walks we know a lot about, right, in statistical physics and in probability theory. The space we're doing a random walk in is richer than the usual spaces, though they're usually used, because it's a software space. You know, usually you do a random walk, say, on a line, in 2 space, in 3 space. Another feature of this random walk is that it's what's called a hill climbing random walk, because we are thinking of what is called in population genetics a fitness landscape, which is a mapping from each organism to its fitness. So you can think of what evolution wants to do is go uphill, go to fitter and fitter organisms. So it's a random walk, but you will reject, you're going to try out mutations, but you're going to reject the ones that don't give you a fitter organism. So you're going to be trying at random to go to from one organism to another, but you're only going to actually do it if the fitness is increasing, if you're going uphill. Okay? So you'll just reject any step in the random walk which is taking you downhill, which is giving you a less fit organism. So this is a pretty simple model. Now, the next important thing to say is, so I've told you what my organisms are, I've told you what their fitness is. One important thing to say, though, is what exactly is a mutation, and what is the probability of each possible mutation that you try out. That's a absolutely crucial step in this, and for 2 years I didn't see the right thing to do. I was using, I think, what are sort of called point mutations in biology, which means localized changes in a DNA sequence. That seemed to be a sort of a natural thing to think about, but I didn't really get anywhere. And the key step in making the mathematics work beautifully and elegantly, which mathematicians, when the proofs come out beautifully and elegantly, and before that you couldn't prove something or the proof was a nightmare, a pure mathematician thinks this has got to be the right way to think about it, right? So there's this experience, this aesthetic experience that convinces you that the ideas are right, and so mathematically at least, the right way to go is to permit extremely powerful mutations, algorithmic mutations, which means a mutation now is not a localized change in a DNA strand, it's a function, it's a program that takes as input the organism, the original organism, and somehow transforms it, can do any algorithm calculation to give you a new organism. Now my organisms are just going to be a string of bits actually. You pick a particular programming language, programs are all going to be bit strings. Remember, that's everything are bit strings yesterday, finite sequences of bits, and here too. So the organisms just look like a sequence of zeros and ones, but they are programs. You have to pick a programming language that gives meaning to that sequence of zeros and ones. And there's a fixed programming language that I do pick that comes from the universal Turing machines used in algorithmic information theory. So those are languages that I know a lot about. Okay, so now the next, so a mutation is an algorithm. It's a very general concept of mutation, and this means that you can now do global changes in transformations in an organism. For example, I can flip every bit. I can change every 0 to 1 and every 1 to a 0. I can make a global change across the whole organism, across the whole program. Now, this is a change that is possible with point mutations, with localized mutations. Localized mutations can be just changing 1 base, changing 2 bases, changing 3 bases. As the number of bases increases, the probability drops exponentially. It is theoretically possible to change, to flip, to change the whole thing, but it's infinitely unlikely. But with this kind of mutations, you see, the whole point is it's always possible to go from any organism to any other organism, no matter what mutation model you pick. But the probabilities will be radically different. So here, flipping every bit is a very simple transformation. The program that does it is very simple. Therefore, this will be a highly probable mutation, which will be tried very frequently. Now, of course, usually it's not a useful thing to do. If you flip every bit in a program, in every programming language I know, the program will be garbage after that. But that's okay. You try out every possible mutation. So So the whole point is algorithmic information theory since the 1970s knows how the natural way to associate probabilities with programs, with algorithms. And the natural way is you use self-eliminating programs, and then a k-bit program has probability 1 over 2 to the k, because every bit is generated by an independent oscillator coin. This is the way you define the halting probability, which is sort of the star of algorithmic information theory. It's this natural example of a irreducibly complex object in pure mathematics. So the same way that the halting probability is believed to be omega number is believed to be defined in a natural way, this pure mathematicians who've worked on algorithmic information theory will consider to be a very natural probability to associate with a mutation. And there are arguments that I don't have time to go into as to why this is a natural probability distribution, but okay, so one thing to say though is, this bit flipping mutation is very probable, but the mutation will be tried, but it will never work. It only works if your new organism is fitter than the original organism. That is to say, if it calculates a positive integer and the positive integer is bigger than the previous positive integer. So now one thing to point out about this